Hello, friends. I hope it's a beautiful afternoon wherever you are, or it's a good evening wherever you are. I know some of you will be watching this from Congo, Goma, where there could be some conflicts. Some of you could be in other countries, but wherever you are, I hope life is treating you very well. Yeah, welcome to this yet another episode of Learning Physics with me. My name is IBM, and today I want us to conclude on what we call the temperature as we move to lesson number 3. So let's strictly move to lesson number 3, temperature, lesson number 3. If you have not considered subscribing, do not forget. Okay, so in lesson number 3, we are strictly going to talk about thermal capacity or heat capacity. In this lesson, I want us to talk much about thermal capacity or heat capacity. We have already seen specific heat capacity, that we use the small letter C for specific heat capacity. Now we are going to talk about thermal capacity. Remember, we use the small letter c for specific heat capacity, and we said the amount of heat required to raise or to change the temperature of a substance by 1 Kelvin. To be specific, the amount of heat required to change the temperature of 1 kilogram mass of a substance, because we said the word specific in this case was meaning per unit mass. That amount of heat required to change the temperature of 1 kilogram of a substance by 1 degree Celsius or by 1 Kelvin is what we call the specific heat capacity C. Remember, I mentioned that a change in temperature on the degree Celsius scale, that is, change in temperature on the Celsius scale, is the same as change in temperature on the Kelvin scale. So, I could say specific capacity is the amount of heat required to raise or to change the temperature of 1 kilogram of a substance by 1 degree Celsius or 1 kilogram of a substance by 1 Kelvin. Because a change in temperature on the Kelvin scale is the same as a change in temperature on the Celsius scale in magnitude. So, specific heat capacity may be used for a single substance whose mass is 1 kilogram, but I want you to note that often objects may be made of several different materials. So objects may be made of several different materials, and in order to find the change in heat energy, the specific heat capacity and the mass of every substance in the object would need to be known. Think of a saucepan which is made up of both aluminium and maybe copper. So it means to find the heat capacity, to find the amount of the heat energy or the change in heat energy, it means you will need the specific capacity of copper and the specific capacity of aluminium, because the object is made up of two materials. But if you want to avoid finding this or using the specific capacity of each of the material, or each of the material which makes up the object, then you could instead use the heat capacity or the thermal capacity rather than the specific heat capacity of that substance. Because remember, specific capacity looks at 1 kilogram of that particular substance. Then the numerical value of heat capacity of a body is actually the quantity of heat energy required to raise the temperature of the whole object by 1 Kelvin. Here, we skip the idea of using specific capacity. We don't look at 1 kilogram of a substance. It will be hard to look at one particular kilogram of a substance when an object is made up of two substances or two materials. So to avoid that, let's just look at the thermal capacity of the whole substance. So heat capacity considers the whole substance. the amount of heat required to raise the temperature of the whole substance by 1 Kelvin or by 1 degree Celsius is what we are going to call the heat capacity. So, for a body of heat capacity capital C, the amount of heat supplied or required, which I will call delta Q, the amount of heat delta Q, which is required to raise the temperature of the whole substance by 1 Kelvin is what we are going to call the heat capacity. So delta Q is therefore going to be equal to a constant C, capital C this time, times delta theta, where delta theta is going to be the change in temperature. So the amount of heat required to raise the temperature of the whole substance without considering its mass, I mean without considering a unit mass, is what we call the specific heat capacity. So if we try to compare this with the previous equation, that is delta Q is equal to mass times specific capacity times delta theta, we shall realize that the heat capacity C is therefore going to be equal to mass times specific heat capacity. That is the total mass times the amount of heat required to raise the temperature of just 1 kilogram of the substance. That will be the heat capacity. So if you try to link these two expressions, if you try to link those two expressions, remember the units of mass are kilograms, so I'm trying to establish the units of heat capacity. Those of mass are kilograms, and those of specific heat capacity were actually joules per, I think it is per kilogram, then per Kelvin. So you notice that the kilogram cancels with the per kilogram, so the units of heat capacity will simply be joules per Kelvin. Joules per Kelvin. So the amount of heat required to raise or to change the temperature of the whole object, the whole body, by 1 Kelvin is what we are going to call the heat capacity. Rather than using specific capacity, we can now concentrate on using the whole body rather than a unit mass, simply because the object could be made up of different materials. So it would mean we would need specific capacity of each material, which sometimes may not be available. In such cases, then we consider the body as a whole, and we establish the amount of heat required to raise the temperature of the whole substance by 1 Kelvin or by 1 degree Celsius. That's what we call the specific heat capacity, the heat capacity. So heat capacity will be defined as the amount of heat energy required to increase. Sometimes it may be decreased by the sometimes it may be to decrease. Just like even for specific capacity, sometimes it may be to decrease. So the amount of heat energy required to change the temperature of a material by 1 Kelvin is what we call heat capacity. The moment we specify the mass to be a unit mass, then we are talking about specific heat capacity. So I want you to note carefully that for heat capacity we use capital C, and for specific heat capacity we use small letter c. Okay, without wasting time, let's see a few examples. Example number 1. These already have even the answers, so I'm not sure if these answers are correct, but we shall verify. Have your calculator close to you so that you follow through as you watch this lesson. A room has thermal capacity, that is capital C, of 1.2 megajoules per Kelvin. Calculate the heat energy required to raise the temperature of the room from 18 degrees Celsius to 20 degrees Celsius. So you will realize that here the mass is not needed. So from amount of heat supplied is equal to, if you want, mc delta theta, but remember m times small c is heat capacity, so delta q will be equal to heat capacity times the change in temperature. So this will be equal to the heat capacity, which is 1.6 times 10 power 6, because it is given as megajoules per Kelvin. then times the change in temperature, which is equal to 20 minus 18. And that gives us twice. This is 2 times that, which gives us 2.4 times 10 power 6, and that is joules. So that is the amount of heat required to raise the temperature of the room from 18 degrees Celsius to 20 degrees Celsius. Number 2, this was number 1. Number 2, a kettle contains 700 grams of water. The specific capacity of water is 4,200 joules per kilogram per Kelvin, and the kettle itself has heat capacity of 440 joules per kilogram. The kettle and itself contents are heated from 150 degrees Celsius to the boiling point of water, which is 100. Calculate the heat gained by the water. So Roman 1, we have the water, amount of heat gained by the water. Since we have the mass of water and we have the the specific capacity of water, we can estimate the amount of heat gained by the water. So the amount of heat, delta Q, is going to be equal to mass times specific capacity times change in temperature. So this will be equal to the mass of water, which is 700 grams, that is 0.7, specific capacity, which is 4,200. The change in temperature, they say the kettle and its self contents are heated from 150 degrees Celsius to the boiling, no, this is actually not 150, this is 50 degrees Celsius to 150, to 100 degrees Celsius, because we can't heat from 150 to 100. This is a typing error. So this will be times change in temperature, which will be 100 minus 50. So for this we calculate, press the calculator, 0.7 times 4,200 times 50. So this is giving us 1.47 times 10 power. Actually, this is not 150. I think it is 15. I don't remember the origin. I think it was 15. Because in practice, how can this be as high as this? Sorry, let's consider this as 15 rather than 150. Rather than 50, let's consider this as 15 degrees Celsius. So that means I will change this to, let me change this to 15. I think 15 makes more sense than 50. So 100 minus 15 times 4,200 times 0.7. Yeah, this is 15, which gives us 2 point. So this gives us 2.4. Actually, it is 2.499 or 2.5 times 10 power 5. This is power 5 joules. So that is 2.5 times 10 power 5 joules. 0.7 times 4,200 times 85. Yeah, 2.5 times 10 power 5 joules. So this is wrong. The power is wrong. Then Roman 2, for the kettle, calculate the heat energy gained by the kettle. So amount of heat gained by the kettle, because we don't have the mass of the kettle, so we shall combine this mass times specific capacity into heat capacity times the change in temperature. The heat capacity has been given as 540 joules per kilogram times the change in temperature, which is going to be the same, 100 minus 15, that is 85. So 540 times 85. So this is giving me 4.6 times 10 power 1, 2, 3, 4 times 10 power 4 joules. As simple as that. Okay, example number 2. Example number 3 actually. Oh, this is a self-check. So self-check number 1, they have given here aluminium. It has a copper base. It is an aluminium saucepan with a copper base. So these are two, two making the same object. Use the information below to determine the thermal capacity of the saucepan. So here you have to find the total thermal capacity of the saucepan. That is the total heat capacity of the saucepan, because now it has that of aluminium, it has that of copper. So you'll be able to find the total thermal capacity. Number 4 is also yours to try out. Aluminium saucepan, that one we have finished. An aluminium electric kettle has a mass of 1.5 kilograms when empty. The specific capacity of aluminium is that. Determine the heat capacity of the empty kettle. That one you'll find. Specific capacity of water is given as that. Determine the heat capacity for 2 kilograms of water. That one is easy. If the aluminium electric kettle is filled with 2 kilograms of water and the temperature of the water and the kettle is raised from 20 degrees Celsius to 100 degrees Celsius, what is the amount of energy required? Comment on your answer. So remember very well that heat capacity is the same as the mass times specific heat capacity. Heat capacity is the same as the mass times the heat capacity, specific capacity. Or heat capacity can be the same as the amount of heat supplied divided by the change in temperature. So think about this. We have already seen this in the previous slide. Then when it is total heat capacity, that one of course you'll have to add. Number 5 is also yours. A steady stream of air is drawn through a tube which contains 500 watts, a 500 watt heater. Given that the density of air is 1.2 kilograms per meters cubed and its specific heat capacity is 1000, calculate the maximum temperature rise of the air for a flow rate of 0.4 meters cubed per second. The answer is there. You will just be verifying to see if that answer is correct or wrong. You may not, this answer may not be absolute, it may not be very true. You can come up with your own. However, with the right method, you should be able to get the correct answer. A block of copper of mass 0.5 kilograms at an initial temperature of 77 degrees Celsius is placed in 0.4 kilograms of water at 30 degrees Celsius. What is the final temperature when thermal equilibrium is attained? So maybe I can try out this for people because they will be seeing this for the first time. A block of copper of this mass at initial temperature this is placed in 0.4 kilograms of water at 30 degrees Celsius. So you have a block. For the block, you have its mass. Mass is 0.5 kilograms. You have its initial temperature. Let me call this T1 or T block to be 77 degrees Celsius. And it is placed in water. So we have water. The mass of water is 0.5 kilograms. The temperature of water is 30 degrees Celsius. So you notice that the block is at a high temperature than water. what is the final temperature. So when these are put together, we shall need the final temperature, which I will call theta. The block loses heat, therefore its temperature falls to theta. So the temperature difference of the block will be temperature of the block minus the final temperature theta. On the other side, the water gains energy, so its temperature rises above 30 until it reaches theta. So the temperature difference of the water is going to be theta minus the initial temperature of the water. So if we consider no energy loss to the surrounding, then the energy loss, the heat lost by the block, should be equal to the heat gained by the water. If we assume no energy loss to the surrounding, the heat lost by the block should be equal to the heat gained by the water. The heat lost by the block to change the temperature from Tb to theta will therefore be the mass. This will be mass of the block times specific capacity of the block times the temperature change, which is T block minus theta. This should be equal to the mass of the water, specific capacity of the water, then the temperature change of the water, which is theta minus T water. We are interested in the final temperature theta, so we simply do the algebra here and substitution and algebra. So this will be 0.5 times specific capacity of the block, which is copper, that is 400, into temperature of the block, which is 77. Temperature of the block is 77 minus theta. The mass of the water is 0.4 times specific capacity of water is 4,200, then times the temperature difference, which is theta, minus the temperature of the water, which is 30. So we get a difference. Here. Yeah, the simplest way of doing this would be, okay, 0.5 times 400, open the brackets. So this would be 200 times 77, 200 times 77. So this is 15, 400 minus 200 theta is equal to 0.4 times 4,200. So this is 1,680 times theta minus that one times 30. So this is 5,0400. So we collect like terms, simply collect like terms and find theta. Now we'll skip some steps and just find theta. I'll have 50 plus 15,400. Then I divide by open brackets when this crosses 1680 plus 200. I'm finding my value of theta as exactly 35 degrees Celsius. So you can also, because the temperatures have been given into degrees Celsius, so I know that theta will be 35 degrees Celsius. This is what we call heat exchange or energy exchange, thermal energy exchange. One material at a higher temperature loses some of its energy to raise the temperature of another material. You will see such questions in another self-check. So number 6 has been attempted for you. Number 5 is still yours. Maybe there is number 7 for you to attempt. Self-check number 7. In an experiment to measure the specific capacity of water, a student used an electric heater to heat some water. His results are shown below. Calculate a value for the heat capacity. Remember, heat capacity is capital C. Comment on any likely sources of errors. What do you expect to be the sources of errors on the value of C that you have obtained? Number 1, The mass of the beaker is 150. Mass of the beaker plus the water is that. Current in the heater is that. PD across the heater is that. Of course, you know that PD and current will give us the power. Initial temperature is that, final temperature is that, and the time taken is that. And we know power times time will give us the energy supply. So you should be able to find the heat capacity C. Okay, let's now move to what we are going to call the specific latent heat. But before we move to the specific latent heat, we have already seen in one of the previous, or in actually most of the previous lessons, that at times when a substance is changing phase or is changing state, to give an example, from ice to liquid or from liquid water to steam, normally heat energy is supplied, but heat energy supplied does not cause a change in temperature. Our question was, where does the heat energy supplied when the substance is changing state go? That was our question. And we attempted to answer that question by suggesting that the thermal energy or the heat energy which is supplied during a change of state may not change the kinetic energy of the molecules. Therefore, the average kinetic energy of the molecules remained constant. Therefore, the temperature had to remain constant. But that heat energy was not wasted. It was actually doing work against the force of attraction between the molecules. The heat energy supplied was breaking the bonds. And if it was breaking the bonds, then there was an increase in potential energy of the system. So we say literally that the internal energy increased even when the kinetic energy was not increasing. So that heat, because the heat energy does not change the temperature, because we expect that temperature is what we would see physically when we apply heat to a system. But because the heat energy does not change in the temperature of the substance, then we call that heat latent. I said the word latent literally means hidden or concealed. It is hidden. It is like we don't physically see the effect of the heat that is being supplied. We have already established that for, of course, the amount of heat released, it can also be absorbed. So note that these heats, I'm always mentioning one side of required, but can also be taken in, can also be absorbed. So that amount of heat released or absorbed during change of state of a substance without a change in temperature, we have already called it the latent heat. There is no change in temperature. When I see the word latent, I know that I will not see any physical change. So I will not see a change in temperature. So that is latent. We have also seen that the latent heat required to melt a solid to a liquid, we have already seen this as latent heat of fusion. So from solid to liquid, we have already seen it as fusion, and from uh, liquid to gas or vapor, we have already seen it as vaporization. But remember, there is no change in temperature. So the latent heat required to melt a solid without a change in temperature is the latent heat of fusion, and that required to vaporize a liquid. To vaporize a liquid without changing temperature is what we earlier on called the latent heat of vaporization. Let's think of a simple demonstration using a graph. Or before we look at the graph, these are some of the important definitions you have to consider. So we have seen that the amount of heat required to change the state of a substance without changing the temperature was the latent heat. Here we were considering the whole substance. Remember heat capacity, we also consider the amount of heat, we consider the changing the temperature of the whole substance. Now here latent heat, we have also considered changing the state of the whole substance. But then when we specify the mass of the substance, then we are talking about the specific latent heat. So specific in this unit will be referring to per unit mass. Specific will be referring to per unit mass. That is 1 what? 1 kilogram. So the amount of heat energy required to change the state of 1 kilogram of a substance without change in temperature is going to be called the specific latent heat. To change the state of 1 kilogram of a substance without change in temperature is going to be called the specific latent heat. If we are changing the substance from a solid to a liquid and the substance has a mass of 1 kilogram, then that amount of heat required to convert 1 kilogram mass of that solid into a liquid without changing temperature is going to be called the specific latent heat of fusion. 1 kilogram of a solid to a liquid without changing temperature, that is going to be called the specific latent heat of fusion. The specific latent heat of fusion will always be labeled with the letter LF. So for a substance whose latent heat of fusion is given as LF, the latent heat of fusion is given as LF, the amount of heat which is required, that is delta Q, required to fuse or to cause this substance to melt, to change from solid to a liquid, is given by M times the latent heat of fusion. So this implies that the latent heat of fusion F is given by delta Q divided by the mass. This gives us the units as joules for a thermal energy delta Q divided by kilogram, so joules per kilogram. The latent heat of fusion, the specific latent heat of fusion, we therefore have the units as joules per kilogram. The specific latent heat of fusion will have the units as joules per kilogram. Many of these units will confuse you, but when you know how to come up with the expression, then it becomes easier to derive the units. So the amount of heat delta Q required to convert 1 kilogram of a solid to a liquid without changing temperature is going to be called the specific latent heat of fusion. So the units of the specific latent heat of fusion, which will be written as L subscript F. L subscript F, sometimes it's just written as L. L subscript F is going to be, the units will be joules per kilogram for the latent heat of fusion. I'm very certain that you saw that in IGCSE. On the other hand, if we now vaporize a liquid, the amount of heat required to convert 1 kilogram mass of a liquid to vapor without changing temperature is now the specific latent heat of vaporization. Specific latent heat of vaporization. This is normally noted with the letter L subscript V, specific latent heat of vaporization, normally denoted as L subscript V. And this is going to be given just similar to the latent heat of fusion. The latent heat of vaporization will also be given as delta Q divided by M. So the units will still be joules per kilogram. That amount of heat required to convert 1 kilogram of a mass, 1 kilogram mass of a liquid to a vapor without change in the temperature is what we are going to call the specific latent heat of vaporization. So some of these definitions will appear many times, so you need to make them part of you. You can easily distinguish them. When the word specific is there, you must refer to a unit mass. If it is a fusion, it is solid to liquid. If it is vaporization, it is liquid to gas. If it is latent heat, there is no change in temperature. Latent, no change in temperature. Specific, 1 kilogram. Fusion, that is solid to liquid. Vaporization, that is liquid to gas. They are easy to distinguish. So let's see how we can summarize all this by looking at a simple graph. A graph of temperature with the time during heating. We are going to consider heating a solid, starting with heating a solid such as ice. When we start heating ice exists at a temperature less than 0 degrees Celsius. Sometimes it is even negative 10 degrees Celsius. So let's begin by heating ice. So we are starting with ice. which is a solid, and we are applying heat. That is now what is happening between in this part represented by A. So when ice is being heated, before it starts melting, the temperature starts rising from negative 10 degrees Celsius. So this is negative 10 degrees Celsius. And when the ice starts melting, now this is now melting. When the ice starts melting, now this will be at 0 degrees Celsius. We will realize that when the ice is melting, the thermometer shows no change in temperature. Not until all the ice has become a liquid. Not until all the ice has become liquid water that now the temperature starts rising. So the temperature now changes from 0 degrees Celsius to a certain other value when we start heating. So here we are now heating, we are continuing to supply heat. So we are at region C. Here, of course, during melting, we were at region B. Remember, the temperature remains constant until all the liquid has melted. So here we have what we call the latent specific or the latent heat of vaporization of fusion. The latent heat of fusion. So let me remove specific so that it is not necessarily 1 kilogram. So all the ice has melted at 0 degrees Celsius. Now the temperature starts changing. That's why you see in part C, the temperature now rapidly grows from 0 to 100 degrees Celsius. So here the temperature is increasing until the liquid starts boiling. When the liquid starts boiling, the temperature now becomes 100 degrees Celsius, and it will remain 100 degrees Celsius until all the liquid has boiled away. So again, when boiling starts, the temperature remains 100 degrees Celsius until when all the liquid has boiled away. So still here we now have latent heat of vaporization. But from this graph, there are things we need to discuss. Number one. So this one is part A is indicating a decrease in temperature. I can't call part A melting. It is not yet melting because if there is melting, the temperature remains constant. In part B, I can say this is melting because the temperature is remaining constant. In part D, I can call this one is boiling because the temperature is remaining constant. Remember, at melting point, the temperature is constant. At boiling point, the temperature is constant. Here we have at B and D, we know that we have a change of state. There are two things to discuss from this. There are two things to discuss from these observations. Which things are these? So why is A steeper than C? Or what is the significance of A being steeper than C? So it means it takes a short time. This means it takes a very short time to raise, what does that mean? It takes a short time to change the temperature of ice from a certain value to the melting point. That's what it means. And you will notice that D is longer than B. What does that mean? This implies that actually melting is going to take a shorter time. This is going to take a shorter time than boiling. In other words, the liquid will boil for long than the solid melting. If you have ice of say 10 kilograms, the time taken for the ice of 10 kilograms to melt into liquid will not be the same time it will take the liquid water which came from ice to all boil away. So this means D is longer than B, indicating that the time taken, it takes a longer period of time for boiling than it does for melting. It also implies that the latent heat of vaporization is greater than the latent heat of fusion. D being longer than B is also indicating that the latent heat of vaporization is far, far greater than the latent heat of fusion. Remember, latent heat is the amount of heat required to change the state without changing temperature. It will need more energy to change all the liquid into vapor than it would need to change all the solid into liquid. So the latent heat of vaporization is far greater than the latent heat of fusion. And in our previous lessons, we explained why the latent heat of vaporization is far, far greater than the latent heat of fusion. We said for vaporization, there is much work done because the volume change is greater in vaporization as compared to melting. During vaporization, the molecules which are escaping from the liquid have to push back the atmosphere as they escape to the vapor phase. So a lot of work is done during vaporization than it is done during melting. I think at this point we now qualify for some examples. This graph may always appear. I will not talk about E. I will not talk about part E. But the most important parts are A, B, C, and D. Where A, the liquid is change. I mean the solid is absorbing heat, but is not yet melting. B, it is now melting. Then C, the liquid is not yet boiling, but is absorbing heat. Its temperature rises. And then at D, the liquid is boiling. So at A here kinetic energy, because there's a change in temperature, kinetic energy is increasing. At C, there is also change in temperature, kinetic energy must be increasing. But at B, there is no change in temperature. Kinetic energy of the molecules is constant. Potential energy is the one which increases. At D, there is still no change in temperature. Kinetic energy is not changing, but the potential energy of the molecule is the one which is increasing. In all cases, the internal energy of the system increases because internal energy is the sum of the random distribution of the kinetic and the potential energies of all the molecules that make up the system. Whether the kinetic energy is not changing, but the potential energy is changing, the internal energy is changing. Okay, examples number 1. Some of these values of the specific latent heat of fusion and the specific latent heat of vaporization may be useful in some of the examples. These could be useful, maybe. Some of them could be of use. Let's see example. So we need to note them where necessary. Now you notice that actually sulfur, there is no value for sulfur here. You may find out why there is no value for sulfur. Examples number 1. Use the information in the table above to determine the heat energy required to melt 50 grams of sulfur at its normal melting point. So you want the amount of the heat energy required to melt 50 grams of sulfur at its normal melting point. So we know that the amount of heat supplied to melt a substance, delta Q, is equal to the mass of the substance times the latent heat. Since it is melting, that would be latent heat of fusion. So this is going to be 50 times 10 power negative 3, 50 times 10 power negative 3, then times the melting point. At the melting point, the latent heat of fusion of sulfur is 38. So this will be 38.1 from the table which you have seen above. It is 38.1 kilojoules per kilogram. So this will be times 1,000. This will be times 1,000 because it was in kilojoules per kilogram. So when you press your calculator, let me press mine, 50 exponent negative 3 multiplied by 38.1 exponent 3 . So this is giving me a value of 1905 joules. So that is the heat energy required to melt 50 grams of sulfur at its normal melting point. Remember, I've used the latent heat of fusion, specific latent heat of fusion that is given in the previous slide in the table. Then number 2, this was number 1. Calculate the heat energy required to melt 50 grams of ice at 0 degrees Celsius. Now, some of you will use the expression which involves change in temperature, and somebody will add there 0 as the change in temperature. Here, we don't consider any change in temperature because at latent heat, the temperature remains constant. So the change in temperature is 0. So number 2, Roman 1, A Roman 1, the amount of heat supplied or required is going to be equal to the mass times the latent heat of fusion. So that is 50 times 10 power negative 3, that is the mass. The latent heat of fusion of ice from the table, the latent heat of fusion of ice is 330. So this will be 330,000. So this will be 330 times 10 power 3 because in the table the values are given in kilojoules per kilogram. So we can press our calculator again. 50 exponent negative 3 times 330 exponent 3. And this gives us a value of 16,500. You can also check with your calculator. So that is the amount of heat required to melt 50 grams of ice. Roman 2, to evaporate 50 grams of water at 100 degrees Celsius. That is now vaporization. So this amount of heat, delta Q, is still equal to the mass times now the latent heat of vaporization, which is going to be 50 times 10 power negative 3 times the latent heat of vaporization, which is 2260 kilojoules per kilogram. So this will be times 10 power 3 to change it to joules per kilogram. And we now press our calculator. 50 exponent negative 3 multiplied by 2260 exponent 3. So this gives us 11300 joules. So that is the amount of heat. Part B, using your answers to A, determine how many times more energy is required to evaporate a mass of water than to melt the mass of ice. So how many times? We just divide. So the ratio is going to be 113,000 divided by 16,500. So we simply divide, find how many times. So that is divided by 16,500. So this is 6.8, which is approximately 7 times. So it will require about determine how many times more energy is required to evaporate a mass of water than to melt the same mass of ice. So the energy required to evaporate water, 50 grams of water, is 7 times that required to melt 50 grams of ice. We now know why that is true, or why that is the case. Okay. Self-check 2. Now this is yours to try using you may use the table above where necessary. You may use the table above where not given. Calculate the heat required to convert 2 kilograms of water at 100 degrees Celsius to steam at 100 degrees Celsius. Water at 100 degrees Celsius to steam at 100 degrees Celsius. You notice that the change in temperature here is actually 0. So this is latent heat of vaporization. How much heat will change 10 grams of ice at 0 degrees Celsius to water at 0 degrees Celsius? So this is still latent heat of fusion. Okay, can we determine the latent heat of fusion? Can we determine specific latent heat of fusion? Let us see. So determining a specific latent heat of fusion. We are going to use almost the same apparatus that we used in specific heat capacity. Fortunately here now when we are dealing with the fusion, it must be a solid melting. Remember the temperature will not change, so we don't need a thermometer in this experiment. So we shall simply use ice to come up with a simple way of determining the specific latent heat of fusion, because ice is easy and accessible to everyone. So we can use ice to determine the specific latent heat of fusion, or to just describe a simple experiment for determining the specific latent heat of fusion. So in this experiment, we shall need such a simple setup. We need, first of all, we need the mass of the ice which has melted after a certain time. So if we need the mass of ice which has melted, so that means we shall first of all determine the mass of the empty beaker. Determine the mass of the empty beaker, I'll call that M1 for the empty beaker. Now place the empty beaker under the funnel. We have inserted an immersion heater in the funnel, and we have surrounded it with, or we have packed it with crushed pieces of ice. Note that the heater is still off. So when we switch on the heater, when we switch on, you'll always realize that the power supply of the heater will always be the same. Of course, we know that the voltmeter is always connected in parallel, the ammeter is always connected in series. The variable resistor here is always to help us vary the current and the PD, so that we can have different values, or we can determine energy for different masses, so that we cancel out energy exchange to the surrounding. So the heater is switched on, and we are going to collect the melted ice in the beaker for a given time t. So a given time t, we are going to collect the melted ice in the beaker. So we shall measure now the mass M2 of the melted ice in the beaker. Of course, first of all, we get the new mass of the beaker with the melted ice. And now the melted ice will be M2 minus M1. That is after a certain time t. After a certain time t. Remember, the heater is switched on for that time t. So there is a current and there is a voltage. So I'll call this one I1 and this one V1 maybe. If I ignore heat losses to the surrounding, I may not repeat the experiment. So in this case, it means the energy supplied, which I'm going to call Qs, is going to be the power of the heater times the time, which is going to be equal to I times V times the time. If we ignore heat exchange with the surrounding, then the energy supplied all goes into melting the ice. So I would say for no heat loss to the surrounding, I times Vt is going to be equal to melting the ice. That would be the mass of the ice, the melted ice, times the latent heat of fusion. Because remember, for melting, the amount of energy goes into melting the ice. That is Q is equal to mass times latent heat of fusion. So this means we have ignored heat exchange to the surrounding, which means I can find the latent heat of fusion as IVT divided by the mass. However, we cannot ignore heat exchange with the surrounding. So that means for a given mass, I will find the energy supplied to melt the ice for a given mass. So I will have two equations. For the first case, I'll have I1 V1 for a given time t is equal to, maybe I can say for the same mass being melted, times latent heat of fusion plus or minus energy exchange with the surrounding. In this case, I say plus or minus because you are not sure. Ice is at a temperature less than room temperature. Therefore, there's a possibility of ice to absorb energy from the surrounding. So I am saying plus or minus. When um, ice is melting, the most probable or expected the most expected observation is actually when it absorbs heat from the surrounding. So it means the amount of heat supplied, part of it goes into melting the ice, but remember the ice is at a temperature less than the room temperature. In most cases, it gains energy from the surrounding. So many times this will be written as I1 V1 T plus the heat absorbed from the surrounding. All this goes into melting the ice. To overcome the energy exchange with the surrounding, we can repeat this for different values of I and V. So maybe we can have another experiment. So we have I2 V2 times maybe for the same time plus H. This will still be equal to M. Now this will be a different mass and this will also be a different mass, latent heat of fusion. So note that I am repeating this to cancel out heat exchange with the surrounding. Repeating the experiment for different values of I and V, I'm trying to cancel out, or for different masses of melted ice, I'm trying to cancel out heat exchange with the surrounding. Because when you subtract these two expressions, you realize, let me call this one mass. I want a different mass. Mass before or mass, which I don't want to use M1 and M2 because I've already used them. Let me change this to mass empty and mass full. So this will be M1. Empty filled or final. Mass empty, mass final, difference M1. So that I can now use here M1 and M2. For the first attempt, M1. For the second attempt, M2. Now, why do we use the same value of H? Because the temperature of the apparatus does not normally change. The temperature of the apparatus does not change, so heat exchange with the surrounding is considered to remain uniform. I want people to note that. Why do we use the same value of H? Why can't we say H1 and H2? The temperature of the apparatus does not change. Temperature of the apparatus does not change. That means the rate of heat exchange with the surrounding always remains constant throughout the experiment. Because the temperature of the apparatus does not change, the rate of heat exchange with the surrounding remains constant throughout the experiment. The temperature of the apparatus, I think apparatus is double P. The temperature of the apparatus does not change, implying that the rate of heat exchange with the surrounding remains constant. That's why in the first attempt I used H, in the second attempt I'm still using H. The temperature of the apparatus does not change, meaning that the rate of heat exchange, the rate of heat exchange with the surrounding does not change. Okay, let us see the latent heat of vaporization. We have seen that of fusion. Let's also see that of vaporization. Now, for vaporization, we need a liquid which is going to vaporize, or we need to vaporize a liquid. So that means to vaporize a liquid, I think the easiest liquid we shall use is water. So we shall need a beaker of boiling water. In most cases, it can be a calorimeter. We shall need the mass of water which has evaporated, but that is very hard. You can't really measure water which has evaporated directly, but you can measure the mass of the water before, and you also measure the mass after some time. The difference in the mass will be now equal to the mass of water which has boiled away or which has evaporated. So let's think of a simple apparatus as such. We have boiling water and an electric heater. We don't need the temperature here. All we need is the mass. So we can record the initial mass of the water, and we shall record the difference in the mass after some water has boiled away. So record the initial mass of the water and the container using, this is a balance of course. Then now we insert our electric immersion heater in the container, and we are going to allow water to boil at a steady rate, at a constant rate. When water is boiling at a constant rate, the temperature of the apparatus does not change. Heat exchange with the surrounding remains constant. When the water is boiling at a constant rate, the temperature of the apparatus does not change, meaning that heat exchange with the surrounding remains constant. So after a certain time t, we are going to note, first of all, we have an ammeter, so we shall note the current, I'll call this one I1, and we shall note the PD, I'll call this one V1 for the first attempt. The change in mass of water after a certain time t, I'll call it M1. Of course, you first get the mass of the container with the water, then again determine the change by noting the new mass of the container with the water after a certain time t. The difference will be the mass of the water which has boiled away. So note that the energy supplied is equal to the power times time, which is going to be, this time will be I1 V1 times T. That is the energy supplied. This goes into vaporizing the water, but because this is boiling, we expect that the temperature of the water could be slightly above that of the surrounding. So this will be equal to the mass of the water, the specific latent heat of vaporization, plus or minus, I'll add plus or minus, heat exchange with the surrounding. So this will be my first equation. And we can now repeat the experiment for a different change in mass. For a different value of I and V, and a different value of M is obtained. For a different value of I and V, a different value of M is going to be obtained. Let's maintain the same time maybe. So if we maintain the same time, let's say we are doing this again in 5 minutes for a different value of I and V. So we now have I2, V2, so that the change in mass is M2 in the same time t. So now we shall have that I2 V2 times T is going to be, this was M1, so this will be M2 latent heat of vaporization plus or minus H. I am saying when water is boiling at a constant rate, the temperature of the apparatus does not change. Thermal exchange with the surrounding remains the same, is approximately the same. So how do I come up with the latent heat of vaporization? You now subtract the two equations. Subtracting the two equations, if we subtract the two equations, we shall now have that V2 I2 times T minus V1 I1 times T will be equal to M2 minus M1 times LV. You notice that H has cancelled when we subtract the two equations. So I'm not saying that M2 and M1, M2 is the initial mass and M1 is the initial mass. No, M1 is the initial change in mass. M2 is the second change in mass when we repeat the experiment the second time for different values of I and V. So note that very well. So from this expression, you can conclude that the latent heat of vaporization is V2 I2 minus V1 I1 times T divided by M2 minus M1. That will give us the latent heat of vaporization. You may not always describe these experiments in the exams, but these diagrams will appear in the exams and just will be followed with calculations and simple explanations. So having an idea about how you go about with the calculations from the diagram is very important. Okay, lastly, under temperature, I think the only thing that is remaining is talking about heat exchange. In one of the self-checks, there was a question that I attempted, was number 6, and I talked about thermal energy exchange. So normally, when a hot object and a cold object come into contact, we know that heat flows from a region of high temperature to a region of low temperature. So heat energy will pass from the hot object to the cold object to the cold one, so that the two objects reach what we call the same temperature, and that is precisely called thermal equilibrium. Remember, I mentioned in one of the lessons, I think it was thermodynamics maybe, I don't remember, that when a substance, when thermal equilibrium is attained, uh, the temperature remains constant and there is no net flow of thermal energy in any particular direction. When a thermal equilibrium is established, the temperature remains constant and there is no net flow of thermal energy or heat energy in any particular direction. I mentioned and I said you should be careful. It doesn't mean that heat energy is not flowing. There is a flow of energy equal in all directions, that there is completely no net flow of thermal energy in any particular direction. Energy flows at a constant rate in all directions. So heat flows from a region of high temperature to a region of low temperature naturally. That is the second law of thermodynamics. The laws of conservation of energy will always apply, that the thermal energy gained by the cold object is equal to the thermal energy lost by the hot object if and only if we assume that there is no energy loss to the surrounding. That is, maybe the material is perfectly insulated, that there is no thermal energy loss to the surrounding. Let's see a few examples as we wind up. Examples number 1. A mass of 0.3 kilograms of water at 95 degrees Celsius is mixed with 0.5 kilograms of water at 20 degrees Celsius. Calculate the final temperature of the water given that the specific capacity of water is that it is the same water, but 0.3 is at a higher temperature than 0.2. So the one at 0.3 will lose heat, the one at as at the one at is at is the one of 0.3 will lose heat, the one of 0.5 will gain heat. So let's say the final temperature is theta. So for the water of 0.3 kilograms, the change in temperature will be now 95 minus theta because its temperature decreases since it is at a higher temperature. The one at a lower temperature, its temperature rises from 20 to theta. So its change in temperature is going to be theta minus 20. Because the one at a higher temperature, its temperature falls. The one at a low temperature, its temperature rises. So that when a thermal equilibrium is attained, the temperature of the mixture is between 95 and 20. So theta is a temperature between 95 and 20. It is lower than 95 but is higher than 20. So we shall say, of course I know that amount of heat Q is equal to mc delta theta. So I will just do this straight away. The loss in heat by this water will be equal to the gain in heat by the other one. So I will say the mass of 0.3 times its specific heat capacity, which is 4,200, times the change in temperature, which is 95 minus theta, that is the loss, will be equal to what is gained, which is going to be the mass, which is 0.5, specific capacity is 4,200, times the change in temperature, which will be theta minus 20. Note that I am not converting here to Kelvin, but even if I convert, although it will complicate the algebra, converting would mean adding 273 on 95, adding 273 on theta. But remember, a change in temperature on the Kelvin scale is the same as a change in temperature on the degrees Celsius scale. So, of course, this has cancelled out. I don't need to waste time on that. So 95 times 0.3, 95 times 0.3. So here I have 28.5 minus 0.3 theta is equal to 0.5 theta minus 10. So collecting like terms, I have 0.8 theta is equal to 38.5. So 38.5 divided by 0.8. and this is giving me theta as approximately 48.1 degrees Celsius. So that will be the temperature, and the temperature will always be in between the two values of temperature given. So this will be the final temperature. Number 2, a mass of 12 grams, a mass of 12 grams of ice at 0 degrees Celsius is placed in a drink of mass 210 grams at 25 degrees Celsius. Calculate the final temperature of the drink, given that the specific latent heat of fusion of ice is that, and that of the specific capacity of water and that of the drink is that. So here we have a drink. The drink is at a higher temperature. The drink is at a lower temperature. A mass of 12 grams of ice is placed in a drink. The drink is at a higher temperature. So it means the drink will be the one to lose heat, and the ice will gain heat. What will the heat do to the ice? One, the heat will melt the ice. And two, because they have given us specific latent heat of fusion, the ice will melt. So the heat goes into melting the ice. And after the ice has melted, now the heat again goes into raising the temperature of the ice. So there are two things happening here. This was question number 1. I want to rub off this so that I use it for question number 2. So for question number 2, in our solution, we have that the drink will lose heat. So heat or energy lost by the drink. What am I writing? My handwriting is not good, but it is fine. Energy lost by the drink. Part of this energy will go into melting the ice. So part of it is going to be the energy melting the ice, and part of it will now raise the temperature of the ice. So this will be now energy changes the temperature of ice. So the energy which is lost or which leaves the drink, part of it melts the ice and part of it now raises the temperature. Remember, when all the ice has melted, its temperature can now rise. So the energy lost by the drink is given by the mass of the drink, specific capacity of the drink, times the change in temperature. This is for the drink. This will be the energy which goes into melting the ice, which is the mass of the ice times the latent heat of fusion. This is for the ice. This was for the drink. Plus the energy change which changes the temperature of the ice. Remember, this will be mass, specific capacity of the ice, and now this is going to be ice water because it has already melted, so that is ice water. So this will be mass of the ice, specific capacity of the ice water times the change in temperature of the ice water. So this will be the ice liquid, the water ice which has melted. So I will say melted ice. It has already melted, which is equivalent to water now. So we now substitute. The mass of the liquid is 0.2, I think that is 12. 12 grams, is it 0.12? No, 0.0. The drink is 210 grams, so its mass is going to be 0.21. Specific capacity of the drink is 4.2. It is almost the same as water. Kilojoules, so that is times 10 power 3. Change in temperature, its temperature was 25, so it will fall to a final temperature which I'm calling theta. So this will be 25 minus theta. This will be equal to the mass of the ice, which is 0.012 kilograms. The latent heat of fusion of ice is given as 334 kilojoules per kilogram, that is 334 Sorry about this. 334 times 10 power 3, because it is in kilojoules per kilogram. Then, so this is for melting, plus the energy which is going to change the temperature of the melted ice, which is the mass of the ice now, which is 0.012, which is melted. We can assume that the mass does not change much when ice melts to become melted ice or water. So this is 0.012 multiplied by specific capacity of water. Of course, this is 4,200, that is known. And the change in temperature, now the temperature of melted ice will be theta, it will be above zero. So theta, the change in temperature will be theta minus 0. I'm not going to simplify this, I'm just going to press my calculator at once. So you can also check. PCB student, anyway, let me do this for PCBs because they always find challenges in simplifying. So I have 0.21 times 4.2 exponent 3 times, so I have minus 882 theta. I'm multiplying that times 25. So this will be 22050 minus 882 theta is going to be equal to 0.012 times 334 exponent 3. So this is 4008 plus 0.012 times 4,200. So this is plus 50 plus 50.4 theta. Of course, when I multiply this by 0, it will still be 0. So it is just 50.4 theta. Okay. Now collect like terms. Collect like terms. I'm going to add to subtract this from this. I take this one the other side. So I have 50 plus 882. So in terms of theta, I have 932.4 theta. Then I'm bringing this one the other side. I subtract. So 22050 minus 4008. So this is 18042. Now I divide by 932.4. And I'm getting theta as 19.4 degrees Celsius. So when you press your calculator, you are most likely going to come up with that value there as the final temperature. I told you that for heat exchange, the final temperature is always in between the highest, the temperature of the substance which is high, and the temperature of the substance which is low. So it is always in between. It can't be above 25. It can't be below 0. So it should be between 0 and 25. Okay. Hope that is fine. Example number 4. Example number 4. Example number 3 and 4. So a lump of copper of mass 120 grams is heated in a gas flame. It is then transferred to a mass of 450 grams of water, initially at 20 degrees Celsius. So you are going to notice copper is at a high temperature. The final temperature of the copper and the water is 310 degrees Celsius. So the final temperature is 300, the final temperature of the mixture. So we have copper at a certain temperature which is not known. I'll call it theta. Of course, it is the one at the high temperature. So the temperature change for copper will be theta minus 310 degrees Celsius. That is the change in temperature for copper. The change in temperature for water, its temperature rises from 20 to 310. So the change in temperature for water is 310 minus 20. So the energy loss by copper is gained by the water, assuming that there is no energy loss to the surrounding. So we are saying heat loss by copper should be equal to the heat gained by the water. Here there is a change in temperature, so this will be mass times specific capacity times change in temperature. This is for copper. This is for copper, and this will be equal to the mass times specific capacity times the change in temperature, and this will be for water. So this is going to be the mass of copper, 0.12, specific capacity of copper, which is 390 joules per kilogram, change in temperature, which is theta minus 310. This is going to be equal to the mass of water, which is 0.45 because it's 450 grams. Specific capacity of water is known, of course, that is 4,200 times the change in temperature, which will be 310 minus 20. So this time we expect theta to be above 320 because theta is the temperature of copper, which is the highest temperature. So simplifying this, I'll just simplify the right hand side, 0.45 times 4,200 times 290. Then I divide by open brackets 0.12 times 390. So I'm getting a value which is very big, of course. This is very big. Let me check this again. 0.45 times 4,200, then times 290, then divide by 0.12 times 390. Okay, I'm getting 11,000. So I have to take 310 the other side. I have to take 310 the other side. So this will be plus 310. And this is giving me a theta as 12,021 degrees Celsius. So that is the temperature that I am actually getting. You can also verify. You can verify and see. You can verify and see. But this is what I'm getting. This is what I'm getting. So that will be the initial temperature. It would mean that the copper will have to be heated to that. It will have to be heated to that temperature, so that the temperature of water or of the mixture rises to 310 degrees Celsius. Okay, so example number 4. Example number 4. By the way, there could be a small problem with this value of specific heat capacity of copper. There could be a small problem with that specific heat capacity of copper. It could be in kilojoules. It could be in kilojoules, but I think it is fine. That is fine. The specific capacity of copper, I think that is fine. It is not in kilojoules. Okay, example number 4. Steam at 100 degrees Celsius is passed into a mass of 350 grams of water, initially at 15 degrees Celsius. The steam condenses. Calculate the mass of steam required to raise the temperature of the water. So I'm going to rub off this. And I use the same space. So steam is at 100 degrees Celsius. Sorry. Steam is at 100 degrees Celsius. Water mass of that, water is initially at 15 degrees Celsius. So the energy lost by steam is going to be equal to the energy gained by the water. So energy or heat energy lost by steam should be equal to the heat energy gained by the water. That is by conservation of energy. So this will be mass of steam, specific heat capacity of steam, times the change in temperature for steam. This should be mass of the water, specific heat capacity of water, times the change in temperature for the water, delta theta, change in temperature for the water. So we want to find the mass of the steam. Let's maintain it as ms. The steam specific capacity of steam, of course, the specific capacity of water is going to be the same as the specific heat capacity of water, just like the specific capacity of ice is most likely going to be the specific capacity of, not specific capacity. The specific capacity of steam can be considered to be the same as almost the specific capacity of the water. So the specific capacity of steam can be considered to be the same as the specific, when steam condenses, can be considered to be the same as specific capacity of water. Oh, but then steam at 100 is passed into mass of that. Initially at that, the steam condenses. So here we need to bring in the concept of specific latent vaporization. Because when it is from liquid to vapor or vapor back to liquid, it is the same thing, latent heat of vaporization. So that means I must add something. I must add a quantity here. I must add a quantity somewhere here. That is good for you to cross out so that the lesson becomes more natural. So the energy lost by the steam, this is in condensing, and change in what? Because during condensing the temperature remains constant, and then part of it is changing the what? Changing the temperature. Change in temperature of the steam should be equal to the energy gained by the water, which is the mass of the water, specific capacity of the water, times the change in temperature for the water. So the energy used in condensing, that is given by the expression mass times latent of vaporization. So this will be the mass of condensed water times the latent heat of vaporization plus this one change in temperature. This will be the mass of the steam. Of course, this will be the same as this because this is condensed steam. This is, I'll call this steam water, plus the specific capacity of steam water plus, times the change in the temperature of the steam. So this should be called the mass of the water, specific capacity of the water, times the change in temperature of the water. So let's now substitute. The mass is not known, so I'll call this ms. This ms is not known. So I'll put this in brackets. Then I have the latent heat of vaporization. Using the table above, one of the tables above, the latent heat of vaporization of water or of steam, water to steam or steam back to water is 2260,000 plus specific capacity of water is 4,200. Temperature change, temperature is theta, temperature change. We are moving from 100 to 80. So this will be 100 minus 80. This should be now the mass of the water, which is 0.35, specific capacity of water, which is 4,200, times the temperature change of water. So it is 80, 15 to 80. So that is 80 minus 15. I know some people will get 15 minus 80. So this is 80 minus 15. Let me even write it clearly. So this will be 80 minus 15. So we simplify this. Just simplify the right hand side, divide by the left hand side. So you will get the mass as, let me also press my calculator. So I'm getting the mass of steam as 0.0408 in kilograms, which is the same as 40, I think it is 40, what is that, times 1,000 times 1,000, that is 40.8 in grams. So here, because the steam condenses, and again its temperature changes from 100 to a new value, which is 80 degrees Celsius. So for condensing, we think of latent heat of vaporization. The amount of heat which is required to vaporize a liquid to vapor is the same amount of heat which is required to condense the vapor back to the liquid. That's why we have this value here. This is given one of the table above that we saw. Remember I said you may need values from that table earlier on. Okay, I think that one is fine. I think we now qualify for a self-check. We qualify for a self-check. Self-check number 3. Self-check number 3. The temperature of a hot liquid in a container of negligible thermal capacity falls at 2 degrees Celsius per minute just before it begins to solidify. Just before it begins to solidify. The temperature then remains steady for 20 minutes, by which the liquid has all solidified. Determine the ratio, specific capacity of a liquid over specific latent heat of fusion. I think I can do this for people so that they can now attempt the remaining ones. For specific heat capacity, the amount of heat supplied should be equal to M specific capacity times change in temperature. Change in temperature. So this will be change delta theta for specific heat capacity. The amount of heat should go into raising the temperature. The temperature of a hot liquid in a container of negligible thermal capacity falls at a rate of 2 degrees per minute. So I'm going to divide both sides by time. So this will be by time by time. So this will be the fall in temperature per minute, change in temperature per minute. So this means this is going to be equal to the mass times specific heat capacity times 20. So Q over T is MC times 20. Then the temperature then remains steady for 20 minutes. So it means Q is now going to be equal to the mass of the substance because the temperature remains constant. So here we now talk about latent heat of fusion. Here we now talk about latent heat of fusion. So if the temperature remains steady for 20 minutes, so we talk about the latent heat of fusion. So this means that the latent, of course, I don't know the mass. But I'm going to divide both sides by time. I'm going to divide both sides by time. So divide this by t. Also divide this by t. So I'll now equate the two equations. I will equate this equation and this equation here. So I will now have that because I want specific capacity over latent heat of fusion. So I have MC times 20 is equal to MLF over T, where T is going to be 20 minutes because the time is 20 minutes. So I want C over M has already cancelled. So I have C over LF, latent heat of fusion, is going to be, so here I'm remaining with 1 over 20, but then when I bring this 20 at the bottom, so it becomes times 20. That is 1 over 20 times 20, I think. Because this was 20, yeah, I think that is true. 1 over 20. Remember, this is the time is 20 here, but then I'm dividing by this 20 here. So it becomes 1 over 20 times 20, which is 1 over 400. When you press your calculator, 1 divided by 400. So this is giving me a value of 2.5 times 10 power negative 3. And I think this makes sense because the specific capacity is far, far less than the latent heat of fusion. So this is going to be the ratio of the specific capacity over the specific latent heat of fusion. You can also verify this. You can try to check it. So you should attempt question number 6. Attempt question number 6. The heater in an electric kettle has power of that. When the water in the kettle is boiling at a steady rate, the mass of the water evaporates in 2 minutes. Evaporated in 2 minutes is that. The specific latent of vaporization is given. Now note that this is joules per gram. So when I'm using this mass, I may not change this. But when I change this to kilograms, I must also change this. But when I don't change, I know when they multiply each other, grams cancels out. Calculate the rate of loss of thermal energy to the surrounding of the kettle during the boiling process. You should be able to attempt that. 7. 0.5 kilograms of water at 20 degrees Celsius in a plastic beaker is placed in a freezer which converts it to ice in 5 minutes and 30 seconds. Calculate the rate of transfer of heat from the water. Rate of transfer, I think that is power. That is energy over time. Sketch a graph of temperature against time for the situation given above. I think we have plotted, we have a similar graph to this. Then number 8, the specific latent heat of vaporization of water is given as this, megajoules per kilogram. Calculate the energy needed to change 2 grams of water into steam. 2 grams of water into steam at 100 degrees Celsius. The specific latent heat of vaporization. When we talk about vaporization, there is no change in temperature. So you don't need to use 100. Some people maybe now think of using 100 because it is given. When we talk about latent heat, there is no change. We don't consider any change in temperature. The water is at 100 degrees Celsius and is converted to steam at 100 degrees Celsius. The specific latent heat of fusion of water is 330 kilojoules per kilogram. Calculate the energy needed to change 2 grams of ice into water at 0 degrees Celsius. Suggest why the answer is much smaller than the amount of energy calculated in question 8, not in question 9. So we have also explained this in one of the lessons. Self-check number 10. A sample of alcohol is heated with 40 watts heater until it boils. As it boils, its mass decreases at this rate. Remember, at boiling, the temperature remains constant. Assume that 80% of the energy supplied by the heater is transferred to the alcohol. Estimate the specific latent heat of vaporization of the alcohol. So give your answer in joules per kilogram. You are just going to verify if this is correct. And lastly, a block of paraffin, I don't know whether it is the last, was heated gently at a steady rate. Heating was continued after the wax had completely melted. The graph of the figure below shows how the material's temperature varied during the experiment. For each section of the graph, describe the state of the material. A, B, B, C, and C, D. For each section, explain whether the material's internal energy was increasing, decreasing, or remaining constant. Consider the two sloping sections of the graph. State whether the material's specific capacity is greater when it is a solid, or when it is a liquid. Justify your answer. So the graph is on this page. You should tell us whether AB with the state of the substance along AB, BC, and CD. You will now attempt that. I think this is the last self-check under this unit. And for watching, thank you for watching. Now you should watch out for solutions to past paper questions. That will be now general ideal gases, thermodynamics, and temperature. And I hope everyone has their question revision questions at hand. So I will be going through this, and I record a long video for the whole of the questions. Write a short summary for this video. I expect it to be very short because they are just majorly calculations here. And then attempt the self-check questions and submit. Until next time, see you and have a good evening wherever you are, or a good morning wherever you are. Bye bye.